Hello everyone, we'll start with the derivation of electric field on the equatorial line of a dipole. So we'll consider a dipole, a similar consideration with charge q, separation 2a and dipole moment p. So minus q plus q. This is point A, this is point B, distance is 2a. So for the point on the equatorial line, that is this line. So we'll consider a point P with a small positive charge at a distance r, at a distance perpendicular from the center of the dipole. So we'll connect these 2 points. So we know this is A and this is also A. So now we can see the electric field due to the charge at Q will be directed towards this direction, that is EA, and due to the charge at B it will be directed towards this direction, that is EB. Sorry, I'll have to rub this part a bit for the derivation. Dipole moment P. Yes. So this is the electric field due to charge at A and this is the electric field due to charge at B. Now we'll draw a line parallel to AB and we'll extend this line here. We'll use this in the further derivation. So now electric field due to charge at A will be equals to KQ upon AP square. AP square. And what is AB? As we can see, this is a right angle triangle and AP square is equals to R square plus A square. Pythagoras theorem, R square plus A square. So KQ upon R square plus A square. And the direction is shown in the figure. Direction as shown. Now EB will be equals to KQ upon BP square, that is also equals to KQ upon R square plus A square. R square plus A square, and this is also R square plus A square. Now we can see that EA is equals to EB. If we just take the magnitude of both, these both are equal. So to find the net electric field, we'll dissolve the EB and EA components. We have dissolved them already here, this and this. So if this is angle theta, this is also angle theta and this is also angle theta. So we know when we have a diagram like this will be EB cos theta, this will be EA cos theta, this will be EA sin theta, and this will be EB sin theta. We'll make another diagram to understand it better. So if this is the line, this is the parallel line. These two are the main components, and we have dissolved it into this and these two components. So this angle is theta, this angle is also theta. So, and this is EB, this is EA. So it is EB cos theta, EA cos theta. This is EB sin theta, and this is EA sin theta. We have dissolved it here. So now the net electric field will be equal to E is equals to EA cos theta plus EB cos theta. The net electric field is the addition of these two. And as we have mentioned that EA and EB are equal here, so we can write it as 2EA cos theta or 2EB cos theta according to our preference. So we know EA is KQ upon R square plus A square from here, and cos theta will be equal to A upon under root of R square minus A square. A upon under root of R square minus A square. That is A upon AP. So calculating this, we take out K, this is 2A into Q upon R square plus A square to the power 3 by 2. And the direction is along negative x-axis. The direction is towards negative x-axis. And also a point to remember, the direction of the dipole is from minus q to plus q. So the direction of the dipole is in this direction, and the net electric field that we have got is in this direction. Our electric field on the axial line of a dipole is equals to E is equals to Kp, as this is the dipole moment given, upon R square plus A square to the power 3 by 2. But we'll write E is equals to minus Kp upon R square plus A square to the power 3 by 2. Minus, because the direction of the electric field is opposite to that of the dipole, as we saw above. So we add the minus. So now, as we did a special case for the electric field on axial line of a dipole, we'll also do a special case here. Special case is when same R is greater than A. So electric fields become minus Kp upon R square to the power 3 by 2. A becomes 0. So we get E is equals to minus Kp upon R cube. This is the derivation. Also, we'll now draw a graph between E and R. As we can clearly see that E is inversely proportional to 1 upon R cube. So the graph is this. We have E on the y-axis, we have R on the x-axis, and the graph is this. This graph is very important for examination point of view. So this is the relation between E and R cube for electric field on the equatorial line of a dipole. So this was it for this derivation. I'll see you in the next derivation. Thank you.